Good morning, everyone. Today we will explore how operating systems handle input or output operations, which are essential for moving data between CPU memory subsystems and devices like keyboard, printer, and disk drives. First, we will look at programmed I/O, where the CPU directly drives each transfer, and then we will examine I/O interfaces, specialized modules that abstract device details and offload work from the CPU. By the end, you will understand the trade-offs and why OS designers choose one method over another. Programmed I/O, also called programmed controlled I/O, is a technique in which CPU issues explicit instructions to the device's register to start each transfer. Every read or write goes through the processor. It tells the device what to do and then watches its status. The operation proceeds in four basic steps. First, the CPU executes an I/O instruction to initiate a transfer. Next, it polls the device status register in a tight loop. This is called a busy waiting. When the device is ready, the CPU moves one word or byte at a time between the device's data and register and a CPU register. Finally, it repeats the polling and moving data until the entire block is transferred. This method has several key characteristics. It is CPU-borne because of the processor waste cycle polling rather than doing other work. Hardware is simple, needing only data and status registers. However, throughput is low, especially for large or fast CPU transfers, since each word requires a CPU instruction. Despite its inefficiencies, programmed I/O remains useful for small or infrequent transfers, like reading a keyboard or simple sensor, where the overhead of more complex hardware isn't just justified and data rates are low. Switching to I/O interfaces, these modules act as intermediaries between the CPU memory bus and physical devices. They handle differences in electrical signaling, timing, and protocols so that the CPU can use a uniform method to talk to every peripheral. An I/O interface typically contains data buffers or registers for staging data, control logic for sending commands and handshaking, an address decoder to recognize the CPU requests, optional interrupt circuitry to notify the CPU when the work is done, and a bus interface to bridge between the system and device protocols. The core functions are command execution, receiving control words from the CPU, and kicking off the device's action. Status reporting through status bits, data formatting, or conversion if needed. For an example, character encoding, and handshaking to synchronize the data flow between components. There are two main types of I/O addressing. In memory mapped I/O, device registers share CPU's address space and are accessed like normal memory load instructions. In port mapped I/O, there's a separate I/O address space and special CPU instructions like in and out, read and write device ports. When evaluating an interface, designer looks at buffer size. Larger buffers support burst transfers and reduce CPU stalls, and whether the module includes a DMA controller to handle bulk data movement directly into the memory, freeing the CPU for other tasks. This balance of throughput versus latency is very critical. Finally, operating systems rely on device drivers tailored to each interface register, layout, and protocol. The interface abstract hardware quirks, giving higher-level OS modules a consistent API for I/O, which simplifies resources management and improves portability. In summary, programmed I/O offers simplicity at cost of CPU time, while I/O interfaces provide richer functionality like buffering, interrupts, and DMA to boost performances. Understanding these mechanisms is key to designing efficient, responsive systems. Thank you.